Hello everybody, hope you all are doing really well. Today we'll talk about a new problem and it states that we need to find the kth smallest element in the array. Okay, so what does the problem say? That we are given an array of some size n and we have to find the kth smallest element in the array. We can understand this better with the help of an example. So here we have an array and it has 8, 7, 32, 11, 10 and 4 as its elements. And we have to find the third smallest because k is equal to 3. Okay. So we have to find the third smallest element. What would it be? Right? So first we'll look into the array. We'll check for the first smallest element which is 4. Okay. Then we find the second smallest element and it's 7. Then third smallest element is 8. So I know the answer is 8. So what did I do actually and what would you have done? You would have thought of how to sort this array, right? Once you sort this array, you can easily identify which is the third smallest element. That's what I've shown you here, okay? Here you're going to sort it, okay? I've sorted this array and now you can tell me what is the third smallest element. It's nothing but 1. This is the first, this is the second, this is the third smallest element, right? We start from the beginning because you have arranged it in ascending order, okay, from small to big. So we know that if we sort the array, we can return the k minus 1 element, right? Because this is 0 based, you have to do k minus 1. Third will be the element at the second index, okay? So that is pretty simple. We can use the sort function to do this. And that entire thing which we're using the sort function and doing will take me O of n log n, okay, time complexity. Instead of doing this, I will use a data structure. You would have heard of a data structure called as min heap, max heap, right? Using a priority queue. So what does this priority queue do? Right? We have elements like 8, 7, 32, 11, 10 and 4. So a min heap, the main aim of the min heap is to keep the smallest element on top of all the other elements. Okay. So now how does the min heap look like? Let's see. So the smallest element is 4. Okay. Then what is the next smallest element here? Next will be 7. Okay. Smaller than that would be what? The smaller elements will come on the right side. Okay, so that is what I'm trying to do here. So we have an 8 here. Okay, then we have after 8, what do we have? We have 10, right? So 10 should come here. Okay, after 10 we have 11. 11 will come here, and then we have 32. Okay, so somewhat the min heap will look like this, right? So this is the min heap and I'll try to extract the smallest element from the top of the entire stack. The smallest is what? 4. That comes. That's the smallest one. After that happens, it rearranges itself, okay? And it ensures that 7 goes on top, okay? That's how it works. It automatically sorts all the elements in the correct order once you remove certain elements also. So we can use that to our advantage. So I've used a priority queue here and this is written C programming, C++. Okay. So in that to declare a min heap, I have to use this greater int also parameter. So this makes it a min heap. So min heap means smallest element will be on top. Okay. Smallest is on top. Okay. Okay. Now what will I do? Now I'll push all the elements into the min heap. Okay. Once I push all these elements into the min heap, it'll form something like this. Okay. With the smallest element on top. Now what do I do? After I do that, I will remove some elements. Okay. So here I want the third smallest element. So I'll remove the topmost element, okay? That will be the first smallest, right? So I'll remove it. Once I remove it, the next element which will replace 4 will be 7, okay? 7 will come on top, right? So 7 will come on top and the data structure will look something like this, okay? I have 11 and 32, right? Okay, now what I'll do, this is the second one. I don't want this also. So again I remove this. After I do this, again I'll rearrange in such a way that 8 will come on top. The next smallest element will come on top. And that is our answer, right? So how many times did we remove the topmost element? Twice, right? First we removed 4, then we removed 7. After we remove 2 elements, the third element will be the top one, right? So you have to return that. So that is the exact implementation I've done here. So till I'm going to execute this loop k minus 1 times. Okay, if it's 3, then I'll pop the elements 2 times. After this, I have to return the top of the min heap. Okay, so I've named it as q. So the q. Okay, let me remove this. It's not neat. So let me just okay, let me just type it out here. So after we do return, after this return q dot top. Okay, this will give me the required answer. Let me just make it a little bit bigger for you. So yeah, hope this is visible. So this should come here. Okay, have to return the topmost element. So that is how we implement the first one way of implementing this entire solution. The next way is to use a sorting algorithm known as quick sort. Okay, and by the way, this previous implementation, the time complexity is log of n. How do I know it's log of n? Because priority queues, the time it takes to insert and remove elements is log of n. Okay, so this is the time complexity. Another way, and we're using some space here also, correct? We're using a queue of size n. Both are being utilized here. The second method involves us to use a sorting method which sorts only till we find the kth smallest element. So suppose if we want to find the third smallest element, we only sort the array till we get that. After we find the third smallest element, we don't need to sort the rest of the array, right? It's just a waste of time. If I want the first smallest element, I'll ensure that I pick the small one and then leave the rest because I really don't care if the rest of the elements are sorted or not. So this algorithm keeps such a thought in mind and it sorts the array. So how does it work? Okay, so the partition or the quicksort algorithm utilizes a pivot element. Okay, so usually we take the pivot element as the last element. You can either take it as the start or the last element. I'll take it as the last element. Okay, so this is called as the pivot. So based on the value of the pivot, we're going to divide the entire array into two halves. Okay, so we want to divide it in such a way that all the elements which are smaller or equal to pivot will come before it and the ones which are greater than it will come after it. Okay, so that is the idea. So what we'll do is we keep an I pointer. This I will keep track of all the elements which are smaller than pivot. Okay, and the j value will be just traversing throughout the entire array till it reaches the pivot. Okay, so that is what we're trying to do. I, j and pivot. Okay, these three are the main things which we're going to utilize. Okay, so let's see how it works. So at the starting we have I pointing here as well as j pointing here. Okay, so first thing we do is we check if the jth element, which is 5, is less than or equal to 4. Is it? 5 is not less than equal to 4. So what I'll do, I'll simply move the j pointer forward. Okay, I won't move the I pointer, I'll only move the j pointer. Okay, and now I check if this is smaller than 4. No, it's not. So again, I simply move the j pointer. Okay, now I check if 2 is smaller than 4. Yes, it's smaller. Once I identify that that element at the jth position is smaller than the pivot, I will swap the value with the value at the ith position, because I is trying to keep track of all the elements which are smaller than the pivot, right? So that is why I will swap it. Now we'll have a array of 2, 8, 5, 7 and 4. Okay, j location will be here itself because you've just swapped it and you have to check with the new value, and the I will move to one position because we know that 2 is smaller than the pivot. You have to check for the next smaller element than the pivot. Okay, so that's why I've moved the I pointer. Now again I check if j is less than equal to 4. It's not, so I move this one step ahead. Again, I see if j is less than equal to 4, 7 is less than equal to 4. No, it's not. I come to the end. I come to the pivot. So this loop ends. So now, where has I stopped? The position at which I has stopped is the location of the pivot. Okay. So this way, I finds the exact location at where the pivot should be. Okay. So this is how it happens, right? So 4 is in the correct position. So that is the entire way how this algorithm works, okay? So that is what I've utilized here. This piece of code does the same thing. It keeps track, j moves throughout from the left to the right of the array, and I starts from the start of the array. And the pivot is always taken as the end element, right? So that's why I've taken AR out of R. R is the end, L is the start part. So as long as the element is lesser than equal to j, I keep swapping, right? That's what I did. As soon as I found out that 2 is actually less than 4, then I swapped 5 and 2. So I swap it and I incremented I value here. I moved it to 8, right? Yeah. And after all of this is done, I have to swap the I and the j, I and the R position, because I know the index, the position I is the place where I actually have to put the pivot element. Okay, so this is how it does the sorting. And now how do we utilize this to find the kth smallest element? Okay, we can use this idea. Whereas here we have L, we are returning what? Excuse me, we are returning the position of this I. Okay, we're returning I here. Okay, and all we have to do is we have to check if I is the kth smallest element which we needed. Okay, we have to check that. So that is why once we call the int pause, in int pause you're going to call the partition, which is this algorithm which we just discussed. We check if that value is equal to k minus 1. Okay, here I've done pause minus L meaning the starting index value. If it's equal to k minus 1, that means that we have found the k smallest element. So I'll just return that element. Okay, but if I find that no, whatever value I've returned is actually smaller than the kth smallest. Suppose I wanted third smallest, but what is pause minus L is, suppose if it's 5, 5 is greater than 3, right? So we don't want the fifth smallest, but we need the third smallest. So what we have to do? We have to ensure that we search in the lower half of the entire array. So that's why I will recall the same function kth smallest, but I'll change the end because I want to search in the starting part of the array. So I'll pass the array, I'll pass the starting position, and then I'll pass the position minus 1 because I want to search for the kth smallest in the left half, lower half of the sorted array, right? If you want to find the third smallest, and you're looking for fifth smallest, it means that you have to move towards the left, right? To the left hand side you have to move. So I'll decrease it. I'll search from the start till the 4 index and search if I can find the third smallest element. Okay, so that is what it's doing. If it's greater, I'll search in the left half. If whatever value I've returned is small, I need third, but I'm showing only one, so I have to search in the right half, right? So that is why I'll recall the same kth smallest function. I'm going to pass the next position, okay, and then I'll pass the end, and then I'm not going to pass k minus 1 here. Why? I'll explain. So okay, so suppose I have an array here. Okay, let me just select this. Okay, so I have this array here, and this is the first, this is the lower half, this is the upper half, right? Let me make it bigger. Okay. So yeah, hope this is visible. This is what I'm trying to do. If the position which we have is actually greater than what we want, right? We're going to search for the lower half. Okay, if the position what we have is actually greater than what we want, position we have is greater than the position we want. So we have to check for the lower half. So I'll search in this part of the array, which is 0 and pos minus 1. Okay, and I'll search for the k element. Okay, that is what I'm trying to do. But here, when whatever I have, if it's reversed, if the position I want is greater than the position I currently have returned here, I need to search in the upper half. Okay, the upper half will be pos plus 1 and ending at r. Okay, so that is what I've done here. But the k minus 1 is actually with respect to what? Start of the array, right? But when you're searching for the in the end of the array, the value won't be k minus 1. It'll be something else. So how do we find that out? I'll just show you. So it'll be I plus pos of L, pos minus L, okay, which is equal to k minus 1. Okay, because this k minus 1 in this starting, you can say that, okay, this is the, suppose if I say k is equal to 2, then you know that, okay, this is the k minus 1 element, right? But now suppose this part of the array I've removed, I'm only searching in this. So if you have to find the second smallest element, you have to search from this new start, right? This new start will be some I. So that's I've done I plus pos minus L will be the k minus 1 element. So what is I? Okay, we have to find what is the I. So I will do simple math. K minus, get pos plus L minus 1. That is what I've written here. Okay. So in the second half, we have to search for this element. Okay, because there's a shift. Because the start is not 0, it is some start position will be some I. So that is why I've tried to use this formula to find out that k minus element in the second or the upper half. Okay, so this is the entire implementation of how to find the k smallest element using the quicksort of the partition algorithm, which is sounds like a big name, but it's nothing. You understood the logic, you can figure out how to write the code for it. It's pretty simple. Just a few lines of code, but it takes time to understand. I agree. I also took a lot of time to understand. And I hope this entire solution does make sense. Okay. So this is the entire implementation. This also quicksort algorithm does take a time complexity of O of n log n. Okay, right? This takes log of n, but it takes a space of O of n. Here it does not take any additional space, except you're doing some recursive call. So if you're considering that, on the worst case, it does call the entire thing n times, because suppose if you have 5 elements and I'm asking you to find the fifth smallest element, which is the last element, it has to traverse through the entire array. Okay, so recursive call will call all again and again till it reaches the end. So it'll call the entire function n times. So that is the worst case. So I hope that this was not too complicated. If it was, also do take your time, go through the entire solution again, and I'm pretty sure you'll get to know it. Take your time and understand the logic, because questions which come in an interview or elsewhere are not exactly the same. So if you understand the logic, that's when you can really apply it in different questions. So I hope it's clear. If you have any doubts, please do ask in the comment section. Thank you. Have a great day.